a brush-like coupler. We shall be designing by doing a calculation on how we arrive at the various dimension and doing the simulation using the Keysight ADS. We'll go through the calculations of obtaining the dimensions of the coupler. But before we go on, we just like to talk a little about the brush-like coupler. The brush-like coupler consists of two parallel lines physically coupled together with two or more lines between them. Here we have three for this particular one. The brush lines are spaced a quarter wavelength apart. You see here, and the main and coupled lines are root 2 of the system impedance. Here we have the system impedance as Z0 divided by root 2 gives us the weight of the main lines. While for the branch lines, we have the weight as the characteristic impedance, which we'll show how to calculate later. The brush-like couplers, they are frequently used as crossovers. So an ideal brush-like coupler theoretically has no coupling between the two parts through it. So our design here is a three branch coupler. We have 1, 2, and 3. Couple which is equivalent to a 3 dB 90 degree hybrid coupler. We have is a combination there is a one. We have a 3 dB hybrid coupler and 2. So the combination of these two 90 degree will give us at the end 180. These are connected in cascade. So this results in a 0 dB coupler, which with input signal, will cross over diagonally to the opposite output. For example, we have an output here. If we have an input here, it will cross over here or this way, and it will give us two outputs here. For example, we have input at port 1, we have output at port 2 and port 3. So it will cross over diagonally. If our input is port 4, it will go port 2 and port 3. So the opposite outputs will be 90 degree with space of 90 degree in both lines. So we'll start now by going through the calculations to obtain our dimension. Like we said before, they have two parallel lines. Each one is a half wavelength length. The branch coupler, they are spread a quarter wavelength apart. So here now we need to calculate what our quarter wavelength is to get the length of this. And this is 1 and there are two there. So the same length here is the same thing here. For this section, we will have here the width. The length will be quarter wave, but our quarter wave will be starting at the middle here, at the middle there to middle here, which we will account for in our calculation. So we start now by looking first to calculate the width of the 50 ohm width. The 50 ohm line, this is our 50 ohm line. Because our characteristics is what we're designing for. We're designing for a frequency of 2.4 gigahertz with a wavelength of 125 mm, using substrate height of 1.6, then the dielectric constant using 4.6, and our characteristic impedance 50 ohm. So here is our we apply our characteristic impedance of 50 ohm and here will be 50 ohm divided by root 2 to get this width. So if we proceed, we know that 50 ohm divided by root 2, it will give us a 35.35 ohm. So these are the two impedance we'll be using. So do a calculation for our 50 ohm microstrip line, and using standard formulas that you can find in any standard textbook, we'll arrive at the weight of the 50 ohm impedance to be 2.97. Here we have to calculate the weight of the impedance, two equations. First one is based on when the weight is less than the twice the height. In our case, we are using a height of 1.6. So if we take here, if we do a calculation and we find, because we don't know the weight, we're going to calculate it. So if we are using a weight that is less than 3.2, 2 times 1.6, 3.2, then we have to use this calculation to calculate. The value we get from this calculation will be valuable. If our weight is greater than 3.2, then the weight we obtain here will be of value to us. So for we applying that, we got the value of A. We'll apply first here. We got the value of A here, which we put into the first one. And after doing the calculation, we arrive at a weight of, for 50 ohm, 2.957 mm. So if we look a comparison, we discover that 2.957 is less than the 3.2. So which means this one is our valid weight which we calculated here. So as we obtained that, we proceed further to calculate the wavelength, the length of the 50 ohm, which we have here. The wavelength of the 50 ohm, which is from here to here. So we move on now using the standard equation we can find to first of all, to get the wavelength, the quarter wavelength, we need to first calculate the effective, what they call the effective permittivity, the effective dielectric constant. So this we calculated by putting our value here. The weight we obtain from there is what we apply to here, the WA50 weight, to get our effective dielectric constant of this value. So we now put that 50 ohm, put that value in to find our quarter wavelength, which is the value of our wavelength, which we obtain from the frequency, from speed of light divided by the frequency. That gives us the wavelength. So doing this multiplication too, we arrive at the length, the quarter wavelength of the 50 ohm section to be 0.806 mm. So having gotten that, we now proceed to calculate the width of the 35 ohm, the 35 ohm line. That is on this side of it. This is I'm referring to now as my 35. This is my 50 ohm, because here is 50 ohm. So this is 35 ohm. That's 50 divided by root 2 give 35 ohm. So the width of this is what we now call W35, and the length of this we'll call WL35. So going back to calculating the weight, we now put that values like previously. Here we have two conditions too, for when the weight is less than 2 times the height, the substrate height, that's 2 times 1.6, and we have when the weight is greater than 2 times 1.6. So having done the first calculation, we calculate for A, we now arrive at 835 of 1.149. So we put that value into the first formula here, first equation, to calculate our W35 using there, and we arrive at 5.077 mm. So we now go back to our equation and confirm our condition. We discover that if for us to use this, our width value has to be less than 2 times the h, so which is less than 2 times 1.6, which that's 3.2. But the value we obtain here is greater than this, so this equation is not valid. So we'll now proceed to apply the second equation and see what we arrive at. So we put in our values, first calculating b with another standard defined equation here, 377 times pi divided by 2 times the characteristic impedance times the root of the dielectric constant. So now we got b, value of b is not stated there, and we now put these values in here for in the second case to do our calculation, where we will now arrive at 5.45 mm. So this value now is greater than 2h, so which means this equation is valid. So we'll now proceed to use the 5.45 mm as the width of the 35 ohm section. So having done that, we move on to calculate the length of the 35 ohm section, and using the same equation as the 50 ohm, but just substituting our rightful values. Okay, this should be 5.45. It should be 5.45 here. So we'll now proceed to do our calculation, and at the end of the day, we got the length of the 35 ohm to be 16.365 mm. So having obtained this, we now fill in our plot, and this is the standard what we'll be using. But we'll make another calculation here to make corrections for our dimensions. So when we are using the ADS microstrip line, so that we'll make adjustment for the size, and because what we're going to be using, this was our calculated value, but we have to make for these tolerances, because we are not starting from here to here, we are starting from somewhere in the middle to this middle. So we need to add these extra values to the value of the microstrip line that we'll be using. Hence, we are subtracting this our quarter wavelength. We are subtracting this length from our quarter wavelength to get the final result we use it for our simulation. So now we'll try to start our simulation by creating a new start a new schematic. Try to put in our values there. So for this, we'll be using the T-lines microstrip lines in some of the models that's part of ADS. So we'll have, let me go back to, we'll need to put this in now. So we'll be using these T-lines, this microstrip lines to define this. So let's just put the values in just the way we have it. Let's put the shape in first, so before we put in the values. So we have So put our inputs here. And now we'll try to define our values here. So what I usually do in this situation, I define here variables so that I can do everything as one go as possible. So here I define first W50, put my W50 values in. Click on apply, 35. Add. So I need to define another one too, which I call L50 divided by 2. But I put 2 there to signify define. So I put my L50 there and divide by 2. And I have L35 as well. That's all I need. Because that's all we need now. So click on OK. And then I'll come here and put in my values here. I have W50. These are my W50. I have to remember to change make sure they are in mm because I'm working with mm. So it's better to just take the mm, copy that. So this will be a different width. I'll have to go through this again later because this is has to be twice this. So make this, we'll change this, come back to this. So we'll have the so for this we have the W35. So we have that section complete. So we need to enter this T line. This is our W1 and this is W2. And W2 is 35. This is our 2, which is 35. Because here you have 1, 2. This 35 is coming to 2. We have 1 here, 35. No, our 1 here is 35. Sorry, not 2. This is 50, L50. Our 1 is L35. L35, L2, 50, and L3 is the width of the 2 times 50. We'll define that now. So you have 31, or 2, and our 3 is 50 as well. So we have that defined. So here is we have, because this one is rotated, our 1 is now here. No, this is our 1 over here, and this is our 2. So on this side, we have our 1 as F35, our 2 define our 3, we need to define these two. So here we have our 1 35, our 2 L50, our 3 is L50 as well. It's our 3. Define, this is our 1 is L50. Our 2 is L35 and our 3 is L50. We need to make sure our dimensions are in mm because we are working with mm. So without have to define our L, we are using here L divided by 2. So for this short one, we're using this. That was L50 divided by 2. 2. It's L50 divided by 2 here. So we define this as well. As well as this. So I will define that this is our L50 as well as this. So let's see what we have left. We have here L35, M35, not L, W35. W35, not F. I was still on the width, not L yet. Why do I keep writing L? So W now. W50 or L. I need to check on my variables that I was putting L instead of W. So width, not length. Okay, check all of them again to be sure I didn't make mistake. Putting length instead of W. So width now, width. This is L35. It's 35. to define this now. We want to make this the center line is W50 times 2. So now call this W50 times 2. This not give me. Let's correct this. That's 50. So let's go check our values now to make sure everything is fine. Even for me something, by the time we go check the layout, we'll see if it's looking the way it's supposed to. Let's just go through to create the layout. We go to layout up here, you see layout, then in one of the menu you see layout, you go to the first slide there, generate and auto update layout. So if you click on this, they will now ask you to set your, because it was not explicitly defined before, we now set our dimension as mm for the resolution. Click finish and click on OK to create a new layout now where all our, we'll see how our design look in the layouts, or what we call popularly called PCB. So this is how it looks like. Obviously we missed something and it's telling us something is not right. So something is built there. So we'll now go back to our layout and find out where the error is. Yeah, because here we see didn't define this, and that's why it's coming as mail. We didn't define this at all. So our, yeah, we need to define this too, because we're using this value here. So we define our width for this T, center T, as well as this. So now go back to our layout now. See, go on layout, generate and update to see if our design is completed. Yeah, obviously something is still missing. We have something overshooting. So we have to go back there. Okay, let's just do a complete search now instead of going and coming back. Okay, we discovered that we have an error somewhere here. Here is supposed to be L. Well, here is L35 and MW35. Here is L35 and W35. So this is one, our T2. So our W1 and 2 are supposed to be the same as L here instead of W. So that's another error we need to correct. So this is W35. So why this is W35 as well. And because our T line here is connected to W35 and W35 on this side, same there. So if we go back to our layout and generate, hopefully we should be able to have everything working fine now. So that's our directional coupler now, or what we call crossover coupler. So we'll now proceed from here to do a simulation and see how it goes. To simulate this, we need first to create an EM setup as electromagnetic simulation setup, where we have to define our substrates and others. We can go straight here to define our substrate, but I usually like to go through EM so we can set up all the parameters too. So if we click on that, I just go for the default, create EM setup. Here we have, because the substrate is not yet defined, so it's giving us an error there. And so we'll now go straight to create our substrate. Here, because we don't have anything, I will click on new. I just create substrate. So we're using FR4 for our substrate. If you click on this, because we have here, this is air, and that's our strip, the micro strip here, our radiator there, and this is our substrate on top which the radiator will be etched. So we click on the aluminum. The aluminum there is as default 25 mm. We need to change that. So if we go here, if we don't have the substrate already defined before, we can just go here and click here. It will open a new. So here, if it's not defined here, we can select to add from a database. So here we're using FR4. So just look for FR4. We have FR4 with the 4.6, which we use for our design, and click OK. It's now added there. We click OK here. We cannot go back here and select our FR4, which have the electrical constant of 4.6. I will change here to mm and use the 1.6, which we use for our design. So after we change this, we leave every other thing the way they are. Just click save. So you see that I've saved that, automatically is reflected here. So telling us that that one is now defined. So the next stage is to define our frequency plan. That's the plan, our simulation frequency. Because we're designing for 2.4, I'll go for to start the simulation from 1.8 and stop at 3 gigahertz. I'll just change it to 51 so I can have a center value. So this is set now. So in order for me to be able to see the 3D view, I'll now go for output plan, then click all generated frequencies. This ones too enable me to be able to see my design in 3D. We'll see that later on. So I will define this now. I can now click on simulate. our simulation is done now. So we see that we have our simulation. You can see that our results are a little bit off. So what we'll not do, because we're aiming for 2.4 gig, and we see that it's just a little above 2.0. So what we'll now do now, we'll try to optimize the system to see how we can move the S11 from this region up to 2.4. So we'll use ADS optimization module to see how we can improve on this. So what we'll do now, we'll go back to our schematic, or rather, we'll go back here. We'll create a new schematic by copying this one here. Copy this cell. Just leave it as version V1. Okay. So we'll put the new cell, new schematic. It's just a copy of the old one. So we'll now proceed now to set up our simulation here. To start, we need first to add S parameter to enable us to run the simulation. So we define this like as before, as 1.8 to 3, from 1.8 to 3, step 0.01. We can simulate this. Before we draw this, we need first to set up our substrate, because it has to be defined, otherwise our simulation cannot run. So we'll go back to the T-line microchip. You have the M stop there, we just add it there and define it as per our design. So we use 1.6 mm with our substrate FR4 4.6, and we have a turn of 0.001. So that's set up that. So we can run this to be sure that our simulation is as defined. So after simulation, you include a rectangular and checking for S11. It's a dB scale. See that it's exactly like the first one. So we just leave this and now proceed to do our optimization. To do that, we need a second S parameter block. And set it up just like the first one. Because the first one we use for the optimization, and one will be used for setting up the goal. So we need to look for our goal now. There's another module called goal, where our optimization will be defined. So the expression for this, we can double click it to open it. We define the expression here as dB, because we're optimizing for S11. dB S11 using SP. We can use SP1, then for the other one we'll use SP2. So for this, we need to define what we're optimizing. So here I'm using FRAQ, which is our frequency. This FRAQ represents the definition of the horizontal scale of our plot. So that's what we're using now, because we're using between 1.8 to 3, but we want to set up our optimization now at, because we need 4 gig. So we use our dB scale of less than say minus 30, while our frequency now will be using 2.399 G to 2.401, because what we're doing, we want to optimize for 4, so our 2.4, sorry, is the center between these two. So if we click on OK here, this would have defined our optimization goal. And next, we add our optimization module. Here we'll define our we use double click this. We iterate for 2500 so that we'll have enough iteration points, and we can decide to change any of these things, or just leave it the way it is default. So, but we still need to change one. Our final analysis here will be, because we use here SP1, so we use SP2 for our final analysis. That's the value here, 1.823. So this set this up. So have we set this up? The next thing we need to do now is to go set up, define what you want to optimize, the values variables you want to optimize. So we'll go to simulate, and here we have simulation variable set up. There you can no, this is tuning, but you need to go to, because we're optimizing, you need to go to optimization tab, click it, then search for, we're optimizing for W50 and W35, the width of those two areas. That's what we want to optimize. We are leaving the length the way they are, just optimizing just the width. So if we click OK, then that set up the optimization. So what we need to do next is click this button here. This will start the optimization process. You see optimization is running now. So when optimization is complete, automatically it does this. Sometimes if it doesn't do this, all you need to do is you can delete that, add S11 again. Then you see our S11. You see that we have 2.4 gig. So we can check the other. We can check other ones like our S23 or S32. Yes, see the relationship between those two. Consider relation between S13 as well as S13, 12, S21. Basically, just output to input. Or let's make this S31. Just make this S31. So output over input. We plot them. You see the relationship between them. This is our S21. It's a little bit off. Our S2, S31 is over there, and this is, it shows that between S2 and S3 there is some coupling between them. So this is basically what. So what we'll now do, we'll now move over, we've done this to update our design. So we use up to goes on every variable. So if we click OK, our designs will be updated. So you can see that here, because we defined our variables here, and what we have now for our W50 is using 1.689 now instead of what we had before. It's using for W50 using 1.689 instead of 2.957 we have, and for W35 is using 3.214 instead of 5.45 we have. So if we update this, say create the layout for this, just to see how our Yeah. This is what we have. That's the thicker part of it is what we have. So if we try to run the simulation for this, yeah, everything's defined. If we run simulation for this, see, this is what we have now. Same thing. So if you need to further optimize, all you need to do is go back to the variables and reset the optimization. You can change any of the optimization. For example, you can decide to include the length of both the branch line and the baseline, so that if you change the length, of course, when you change the length, your everything changes. So it depends on what your design is for. You can optimize your design just the way we did. I hope this helps. Thank you for watching our video. If you like our video, you can subscribe. Don't forget to click the like button as well. Thank you.